Okay. Let's go ahead and start. I just want to remind you the text for the course is this one. It's available as an ebook or as a hard copy. We do have assigned readings from it. I have mixed feelings about the text. It has some good parts and some bad parts, but I've tried to assign the ones that are related to the things I'll be talking about, and that's the revision I made to the reading list yesterday. I won't be testing extensively from it, but it does have some good background in it and some examples that are from a variety of different things that can go into more depth than I can. So take a look at that. The readings the other readings I've listed, almost all of them have hyperlinks to PDFs. Those are things that you should at least look at and read through, skim through, depending on your interest, to read them in more detail. But in this field, even though we've been doing it 30 years, the leading edge stuff comes out in the journals. There's really still no good texts. So read the journal papers. So I'm going to step back a bit from yesterday, since I did Wednesday's lecture on Monday, April Fool. Talk about some of the background today. Some things that you may not have understood fully yesterday when I was talking about things. I'll cover those in a little more detail. Give you the background of some of the different materials. Example pointer here. And again, this is just a quick review. There's a lot more detail available. I'll try to give you the key points. And of course, it's from my perspective as a geologist. The most important things are the geologic materials. That may not be your main interest. I've tried to cover a little bit of each area here, and if you want more of the literature, is the place to go for. I can answer questions. So in this particular section, in most of the course, we're really talking mostly about the VNIR and SWIR. I'll talk about long-wave IR tomorrow. We will look at some long-wave IR hyperspectral data in lab, and I'll try to introduce you to some of the things that are important for that. In these wavelength ranges, absorption is the main thing that we're talking about, where things, the radiation interacts with the molecules, basically, of the materials. And we'll see spectral features, which I referred to yesterday as absorption features. These are the low points in the spectral curves, the reflectance curves, that give you information about what molecules are interacting with the light based upon the wavelength position of the features. There are a lot of spectral libraries, and that's where we go to build the knowledge of what things look like in this particular spectral range. And by the end of the term, I'd expect that you'd be able to look at the spectrum and be able to determine at least what broad class of materials it falls into. Is it geologic? Is it vegetation? Is it water? Is it man-made? And in some cases, some of the detail of what particular material it might be in that group. One thing I'll talk about at the end, maybe probably fall into tomorrow based upon timing, is spectral variability, and there's still not a good understanding of spectral variability and how it affects where absorption features occur and what they look like. I have some information about it. I'll give you what I know, but it's still an area of open research. There's just not like a fingerprint that's the same every time that you see it. The signature has a high amount of variability to it, and it changes depending on the circumstances and what it's mixed with and some other things. And then, of course, we have the atmosphere, which I alluded to yesterday, that while we can measure high spectral resolution signatures in the lab and in the field, when it comes to measuring them from airborne systems or from satellite systems, the atmosphere is a key component, and it blocks completely, in almost all cases, the light that reaches the sensor at 1.4 and 1.9 micrometers. So those regions are not useful for remote sensing, except in very rare cases, unless it's because it's actually saturated, or the atmospheric absorption bands fully absorb all of the energy, except at very high altitudes. So in this wavelength range, we're talking about solar radiation, and the photons interact with the surface on a molecular scale. There are certain things that happen in molecules. I'm not going to go into any detail, but I'll show some examples of how the energy interacts with the molecule, and there's only certain energy levels that can be occupied in certain types of absorption features, so we know what to look for. The absorption of the energy by the molecules is what causes these features, so it's absorbed selectively by the molecules, and it makes the molecules move and stretch and bend in ways I'll talk about in a minute, and that energy then is not returned in the reflectance signature. One thing that always comes up when you talk about remote sensing in the visible near infrared and shortwave infrared is, can I see what's below the surface? And people would love to be able to penetrate into the material and be able to see something below it, but we're restricted in almost all cases to just the very thin portion of the surface, around 50 micrometers or less penetration. And so a coating on a rock or a paint on something conceals what's underneath. You only see what's on the very top. And of course, in addition to that, if we're trying to look at the Earth's surface, and 70% is covered with water and another 25% is covered with vegetation, there's not much Earth's surface to see beyond that, because you can't see through the vegetation with passive remote sensing, with hyperspectral remote sensing, although there are LiDAR type things being developed, even multispectral and hyperspectral LiDAR in the future that will give you some penetration. So the sun's our source. The energy comes down. Some of it's reflected from the Earth, some of it's absorbed by the Earth, some of it's emitted by the Earth. There's light that never reaches the surface. You have to take that into account. That light in the atmosphere that's scattered back to the sensor without ever reaching the surface is an important component of what we have to correct for in order to get a surface reflected spectrum. So you've probably seen all this before. The incident light, reflected light, scattered light, some of it transmitted and refracted, some of it absorbed and emitted. So these are the basic parameters that you saw in physics 3052, the way that energy interacts with matter. And so it's this and this that we're most interested in, this wavelength range and the emitted energy in the long wave, mid-wave and long wave IR. I'll define what those are. Just to define some terms, radiant flux is the total power incident on a surface. The radiant flux density has to do with the surface area. Excidence is how much of the energy leaves the surface. For surface area, again, measured in watts per square meter, and this is all from Jensen, its basic definition terms. Just be aware of those as I speak through. I really won't talk too much about those terms as we're talking about the imaging spectrometer data. Mostly I'll talk about radiance or reflectance. And radiance then is the flux per unit over solid angle leaving a body. So it's over in some direction. Okay? And that's the formula. It describes the strength of the solar radiance reflected or emitted by a surface in watts per square meter per steradian. So it's over some angle. You might also see it in microwatts per inverse centimeter per steradian or something like that. And you have to be careful about that when you're making atmospheric corrections, because you have to know, once you get a radiance image, you have to know what the units are in order to know what to plug in to the atmospheric programs that make the correction to reflectance. So pay attention to those units. Reflectance, then, is the main thing we'll be dealing with in this wavelength range. Is the ratio of the amount of light reflected to the total amount of light incidence. Simple equation: how much comes in, how much comes out. It's a percentage from 0 to 100, or you'll see it from 0 to 1. In the imagery data, you'll often see it 0 to 1,000, 0 to 10,000, where it's been multiplied by some factor to try and keep the data in, or store the data in an integer form to save space. And then that's dimensionless. And what we're looking for then is some wavelength range, usually on the x-axis, and then reflectance from 0 to 1 or 0 to 100% or 0 to 10,000 or 0 to 1,000 with some multiplier or gain applied. And we're interested in how the reflectance changes with wavelength.
Why not use a digital number as your y-axis?
Well, because we want to be able to compare between scenes. The digital number is not directly related, it's proportional to reflectance. But when we measure something with a field spectrometer in the laboratory, we're getting that return in reflectance units between 0 and 1, and we want to compare to that.
So how do you know the initial incident light on the surface outside the lab?
You have to use some kind of standard.
Okay.
That's a really good question. So in reflectance spectroscopy with a laboratory or a field instrument, measure something that has a known reflectance, usually a reflectance of about 1. And we use, for most of the stuff we do in this wavelength range, we use a material called halon, which you're probably familiar with. It's used in fire extinguishers.
Sure.
And it's very bright white. If you look at the reflectance, or the signature of that, it's very flat, and it has a bright reflectance. And so you standardize that to that measurement in the laboratory or in the field.
So you take your sensor image, halon, and then that's your new baseline?
Yeah. And that's not often done. Well, I guess more often it's done in calibration of sensors. In the past, it was just they didn't measure that standard, and you would just calibrate, or not really calibrating, but comparing to some reference standard in the image. So you pick a bright spot in the image, you divide by that, and that's your relative reflectance. It's not absolute reflectance. It's relative to some surface.
Could you use stuff like asphalt mobile?
Well, asphalt's dark, so that presents problems.
So you always need bright.
Yeah, it needs to be bright because you want to have a high signal. If you divide by something with a low signal, then everything's going to be brighter than that, and you're going to have all the noise incorporated from the low signal object that you use. I'll talk about some methods, some empirical methods to make these corrections, as well as model methods. But basically, this says reflectance. That's typically reflectance compared to some bright target, and unless you know the absolute reflectance of that target, then what you're measuring is relative reflectance. It's reflectance relative to some target. The halon standard has been measured by NIST, well characterized, and so if you use the halon, you can get to absolute reflectance. Okay. So there's different types of reflectance, of course. Light can come down and be reflected directly away from you. That's specular reflectance. There's scattering that takes place, as we talked about in SAR, similar sorts of things where you'll get some, first of all, you might get some preferred direction, and then some scattering, or you might have what we call Lambertian scattering, in which the scattering is similar or close to being the same in all directions. This is what we're most interested in. So the interaction between light and molecules and particles happens when the light comes down and it hits some material, and it can either penetrate it once and come back out, or it can penetrate a number of different particles and come back out to the sensor, and so it modifies what comes down, and modifies it by absorbing energy within these particles or materials at certain wavelengths. And that gives us the characteristic reflectance spectra that you'll be looking at all term for a variety of materials. And here I have some examples. It looks like these are rocks or minerals up here, and so they have, the first thing I do, as we already talked about some of it yesterday in advance, is say, where are the main features? What's the shape of the spectrum? And so I can tell immediately that this is not vegetation, right? Vegetation has this feature at around 0.68 micrometers and a high shoulder in the infrared. And so one of the first things I do when I'm looking at a surface is say, is it a rock or is it a plant? And if it's neither, it could be neither one of them. But if it's vegetation, it's very obvious. The rocks have more characteristics, features in the 2.2 micrometer range. So for a rock or mineral, that's where I usually look. There are a few features like this. They're a little broader in the near infrared, around 0.9 micrometers. Those are typically caused by iron. I'll talk about those in a second. But I can immediately say vegetation, not vegetation, 2.2 features, 0.9 feature. These are rocks. Same thing here. These are not vegetation. They have some of the mineral features I've been looking for. Oh, look, very low reflectance out here in the shortwave infrared. This is water. Where's the peak? Peak's in the blue. This is open water. This is shallow water. There's some influence in here of other materials as well. So you can break it into broad groups based upon certain characteristics. Just to remind you again, you've all seen this, where we're working in most imaging spectrometry is between 0.4 and 2.5 right here in these atmospheric windows. And in fact, if you look at, this is atmospheric transmission, you'll see features. Here's the ones I was talking about at 1.4 and 1.9 that are totally absorbing. And then also the third one going out just longwards of 2.5 micrometers that limits us to that 0.4 to 2.5 region. We're working in the atmospheric windows. See, there's other ones out here where there's good transmittance. This is around 3 microns, 3 to 5 microns, the mid-wave IR. This is around 8 to 14 microns. That's long-wave IR. You'll hear different designations of these regions. The ones I use in this class are visible, which is around 0.4 to 0.7, near infrared 0.7 to around 1, shortwave infrared 1 to around 2.5, midwave infrared 3 to 5, long-wave infrared 8 to 14. You may run into other descriptions that are a little different than that, but that's for consistency. Those are the ones that I use. Okay. So let's talk a little bit about absorption bands and what causes them. Electronic processes within molecules involve absorption of photons with specific energies. They cause electrons to move around from a lower energy state to a higher energy state, and that can only happen at certain points. If you know about chemistry and quantum mechanics and those kinds of things, which I don't know much about, you'll know that there are only certain places those electrons can go, and so they absorb certain amounts of energy. In reflectance spectra, we look at and find the minimum and maximum of the curves. The minimum are typically caused by molecular absorption, and we call those features then the low points of the curves. We call them absorption features. I should have told you that yesterday before I started talking about all those features and how to find them. That's definition. General definition of absorption feature. So what processes cause absorption features in these wavelength ranges? There's generally two sets. There's electronic processes and vibrational processes, and there's a variety of different things I'll just talk briefly about in each one. And then in terms of vibrational processes, okay, so these are at wavelengths short of about 1 micron. These are wavelengths between 1 and 2.5, well, actually longer than that. We see the effects of them between 1 and 2.5 micrometers caused by molecular vibrations. The fundamentals actually occur out at longer wavelengths, but we see what's called overtones and combination tones of those at these frequencies. So crystal field effects are the results of interactions between electrons and crystals and in rocks. We know you've all seen minerals in museums and so forth where they have a very nice crystal structure. If there's a good crystal structure, then they absorb light in a certain way. This is in particular particularly true for iron minerals, iron oxides, and those features near 9 microns and here absorbing into the UV at 0.4 are caused by these crystal field effects. They occur for minerals like materials like iron, chromium, nickel, cobalt, titanium, vanadium, and things like that. But iron in the Earth environment is the most important, and it's Fe2 and Fe+3, and the position of the absorption features varies depending upon the valence of the iron electron. So for Fe+3, it's around 0.9 micrometers. For Fe+2, it's usually longer than 1.0 micrometers. Charge transfer is this. I apologize for these plots. They don't look that great, but they're better. You'll see them better if you print out the PowerPoints. It's this usually this range here in the green to UV, the red to UV, and it does in fact result in complete absorption of the energy down here in the UV wavelengths. Again, iron is the most important of these. We see conduction bands and color centers. I'm really not going to talk much about those, but just suffice it to say that they cause color is really kind of self-explanatory. They cause absorption at wavelengths where you see, for example, this one has a peak here near 0.6. That's going to be a red color center. This will be a blue color center, and so forth. Vibrational processes are the most important for the geologic materials and also for a number of other naturally occurring materials. The absorption of energy from photons causes molecules to vibrate. They have bonds, and when those bonds absorb energy, they move. They don't just sit there. And you'll see in a minute my cutesy little cartoon. And the wavelength where these occur is related to the strength and length of the bonds. The principal or primary features occur longwards of 2.5 micrometers. We'll see some of these when I talk about the long wave IR. But we have for some of the key components of Earth materials, we have features between 2.6 and 6, and then we have these other ones that occur at longer wavelengths, and we see what's known as combination tones and overtones of these at shorter wavelengths. So this is just to illustrate the point that molecules don't just sit there, despite the fact that we don't see them, and they're solids. They're moving, these bonds are moving all the time, and when you apply energy to them, the frequency that they vibrate changes. That change in vibration gives you the absorption feature of the absorption of the energy causing that change in vibration gives you the absorption feature that you see in a reflecting spectrum. Here's an example for, this is for water vapor. So the principal features are longward of 2.5 micrometers. We see an asymmetrical stretch where you have a stronger bond here causing this double feature here at 2.6 and 2.7. We have a symmetrical bend here where the features between a couple of water molecules are symmetrical, and you only get a single feature like this. How that applies to us then in the visible or in the shortwave infrared is that we see multiples of the fundamental frequency. They resonate at frequencies other than the fundamental frequency, and they resonate in combinations, which are the sums and differences of those primary bands, and they occur in combinations. So we can see, and these are just the way that the chemists designate the bands, the physicists designate the bands. We add them in frequency, we end up with features that occur at shorter wavelengths. Those are the ones we see in the middle feature. And you need to be able to, particularly if we're working between long wave IR and short wave IR, you need to be able to convert between frequency and wavelength. And it's a fairly straightforward thing to do. The equations there and an example. So if you want to work through that, you'll often see long wave signatures measured in inverse centimeters in frequency. And so you'll need, in order to understand the libraries, which are often in micrometers, you'll need to convert back and forth. And so that's the equation to do that. Fundamentals for liquid water occur at these longer wavelengths and higher frequencies. So we add them, then you end up with this feature near 1.4 and near 1.9. So they're not fundamentals, they're overtones and combinations. And they start to look like this in that wavelength range because minerals and rocks incorporate water. Vegetation incorporates water. Minerals incorporate in a couple of different ways. It can be liquid water, or it can be tied into the crystal structure. And those are usually OH bonds tied with something like magnesium or iron, so you have an MgOH or a FeOH or an SiOH or an AlOH. Those all vibrate in different ways. And that's what you see in these different minerals. I don't expect you to remember all the mineral names, but there'll be some key ones that I'll point out as we go along. And the spectral features. We're principally interested again in this region out here. What do these bands tell me? There's an absorption feature there. What do you think causes it? Well, these are measured in the lab.
So water?
It's water. Yeah. So these are liquid water. What about here? Liquid water, possibly some tied into the structure. When we start to see little small features on the edges of these bands, then it's reasonable to think that those are related to the crystal structure and the way that things are tied in the molecules. So the water is actually tied in as an OH. We'll see things like that in different minerals. But so for these minerals where they have all these nice strong features, what are those useful for? War? Absolutely no. They're useful in the laboratory. They're not useful from the airborne.
What type of instrument is measurements? Like a scale of those?
These are probably measured, I'm not sure of the source. Yeah, those are measured by the USGS in the laboratory with a contact instrument with a powdered sample. Similar sort of sample preparation. They're ground up, sieved to a certain size. It's not compressed into a pellet. It's a loose surface, and it's not in contact with the instrument. The light hits the instrument usually in an integrating sphere, so it's got some coating of halon or something like that on the inside. The light comes in, it's dispersed in a Lambertian fashion, reflects off the surface of this material that's on some opening in the sphere, and that's returned to the detector and compared to a standard. So the ranges here. I should mention this. This is a typical way of displaying spectra with no vertical scale. These are what's called stacked, and NB offers this option to stack them, where it just piles them up on top of each other, so you can compare where the features occur, but you've lost the vertical scale.
You said it's only useful in the lab and not elsewhere. Why is that?
Because, as I'll go into it in more detail in the atmospheric section, but because the atmosphere is basically fully absorbing, it's totally opaque in the shortwave infrared at 1.4 and 1.9 micrometers. I guarantee that'll be an exam question, something related to that. I'll try and trick you and say, what about these features? And you're going to say, no, you can't use those. And you tell me why. You can't, because the atmosphere is opaque near 1.4 and 1.9 micrometers. So a common thing that we'll see in a lot of the earth materials is this hydroxyl vibration, OH. It's common in clays and other altered minerals where the primary mineral has been hit by water, usually hot water, and it changes the minerals and the water bonds with the oxygen in the rock as part of the rock structure, the mineral structure. It has a fundamental feature at 2.7, which comes out to an overtone near 1.4 micrometers. There's also a combination tone at 2.2 or 2.3, depending upon what it's tied in with. So, for example, an ALOH will be at 2.2, and MgOH will be at 2.3. So now you're starting to do chemistry with spectroscopy based upon the absorption features and where they occur. And it goes even beyond that. Oftentimes you can tell the temperature that a material was formed at by the position of the feature. Aluminum is a specific example, that it bonds, different amounts of aluminum go into the material, into an altered rock, depending upon how hot it was, how hot the water was when it went through. And this feature shifts around depending upon the temperature of the material forming it. So you can not only do chemistry, but you can do some geothermometry as well. And we won't go into that in detail, but it's something you should be. The basic idea now is that we're going to start doing chemistry with spectroscopy for geologic materials. We're going to start doing other things for vegetation and so forth. So here's just some interesting minerals. Our favorite mineral, kaolinite. A lot of structure here at 1.9, typical water band, or 1.4, typical water band at 1.9. But the feature of interest is this double feature out at 2.2 micrometers. And you'll see, I said that this is characteristic. You'll see that other features or other materials have features that occur in similar places, like muscovite. But it's a single feature. Muscovite has that, and that. Kaolinite has that, and they're all at different wavelengths and have different shapes. And that can be characterized. Minerals that have magnesium tied into them like this phlogopite is a mica, kinolite is an asbestos-like material. They have these features that are at different wavelengths. If I line my wavelength guide up here, you see these two, this one, and kaolinite line up at 2.2. That one and that one line up at 2.3. That's the chemical difference between them, a ALOH bond versus an MgOH bond. So here's a list, a cheat sheet, so to speak, of where some of the various features occur, and you refer back to that. There's also a common chart that shows in the black areas where features occur for specific materials. You go back to that if you're asked about a mineral. And here's just an example then of selected minerals, which I didn't even label what the minerals are. It must have been in the key wherever I got this from. It's something I did. I can tell you what they are. So this is an iron oxide, and that's these characterized by these broader features here. Note that there's no shortwave infrared features in the iron oxides. If there are, and there are in some of the library spectra actually, and this will be a trick for you to learn too, is that there are no shortwave infrared features in this iron material if it's pure. And if you see them out here, they're caused by something else. So that's something that you'll learn, that retain that knowledge over time as you look at spectra. This would be a montmorillonite. I know that because it has, that's a swelling clay. Bentonite, it's used in pool filters and things like that. It's the thing that cracks buildings when it gets wet. It expands. I know that because it has a 1.4 and 1.9, again, a laboratory measurement. But I could make a pretty good guess at it out here on the SWIR because it just has this single feature and a slope going off to longer wavelengths. It doesn't have any extra features here. Compare that to muscovite, which has a similar feature, but it has these two little extra features out here. Carbonate, CO3, occurring in the 2.3 micrometer range. And then the MgOH, this is probably a chlorite or something like that. And it has that Fe plus 2 at this longer wavelength as well as Fe plus 3 here. So you can start to break down and interpret some of these features. And if you can't assign a name to the material, you can at least say what sorts of chemical bonds are causing the features. Again, that's something you'll gain with experience from looking at lots of spectra. There are some tools to help you with this, and we'll talk about them in class or in lab. There are some things built into ENVI that are kind of rudimentary. There are some things beyond that that I've done that aren't published. Well, they're sort of published in the gray literature, and there's prototype software that you can optionally run to do an expert system where you don't have to actually know all the minerals.
Is there a way to tell a difference between the water and the hydroxyl?
Not really. No, except that the hydroxyl doesn't occur at 1.9. So you have both water and hydroxyl at 1.4. If you have a 1.9 feature as well, that means there's liquid water. So then you have to re-examine the 1.4. But directly, if you were just to look at the 1.4, there's no way to tell the difference. They look very similar. So here's just a bunch of different minerals. I'm not going to talk about them. I just have the reference. Let's talk about soils. So minerals are great, wonderful, and near and dear to a geologist's heart, but how much of the world is covered by pure minerals? And how interesting is it to the sorts of applications that we're trying to do? Probably not that interesting. What we're more interested in is the real surfaces, and that's the more difficult surfaces. We'll use the minerals as an example to learn about spectroscopy and to learn about analysis, but it's really the more difficult cases that are of the highest interest, and that's soil is one of these, where soil is developed. You have the mineralogy, and you see these differences, but it's in there, and it's in the signature, and it's masked. Soils are wet. They have different amounts of water in them. Soils have organic material. Soils have different particle size. They aren't this wonderful, ground up, perfectly sieved, dry, clean sample that we measure for the library spectra. So when you go to match a soil against a library spectrum, it's going to be a lot different. The matches are going to be a lot lower. And there's also things like texture. So typically, the toughest thing in the soils are the organics in the water. These are absolute reflectance relative to some standards, so they haven't been stacked. This is the effect of adding water. So here's a fairly dry soil with 0.8% water. It gets wetter as you go down this way. The soil gets darker. The water features get deeper. Here at 1.4 and 1.9. The feature you're most interested in to know about mineralogy of the soil, here it's suppressed. So it's a lot more difficult to match and to understand what's in that soil because it's not just a simple mineral, it's a number of things, and the moisture highly affects. This one, let's see, trying to remember. These have to do with iron oxide here, organic carbon there, clay here, and carbonate here. Those are common components of soil. And what this is showing is that as the amount of a certain material increases, the absorption bands change in depth. So basically there's not a direct correlation, but there's a relationship between the amount of material in a surface or in a soil and how deep the absorption bands are. Generally deeper in the shortwave IR as concentration increases. There's a number of complicating factors, including moisture and grain size. But generally that's true. The absorption feature depth increases with concentration. Grain size effects. So this is a comparison of a montmorillonite, which is that swelling soil, against a more micaceous soil here. And looking then, if I can remember this one, as the particle size. So this is a similar relationship to what we saw with concentration and why you can't strictly separate concentration. That is, as the particle size increases, the absorption band increases, depth increases. And that holds true for both of those, and that's what these trends are here. So the complication that if you're looking at materials with variable grain size, and you're trying to estimate abundance based upon the band depth, that's not strictly going to hold true because some of the change in depth can be caused by the grain size. Questions about mineralogy in general, and we'll talk more about it all through the course. You'll be saturated with geology more than you ever want to know. And that's as much as I want to talk about the visible and infrared properties at this point. Questions? Okay. Let's talk about vegetation. So that was a nice simple case. The vibrational and electronic processes are pretty clear. The thing about vegetation is that there's really only a limited number of components that put them together, and they're all dominated by water. Even the driest vegetation, not the very driest, but most vegetation down through the succulents has some amount of water in it, and that water overprints on top of everything. The architecture of vegetation has a high impact on the signature. You'll see, so you can measure a leaf in the laboratory. You can measure several leaves in the laboratory and get a different result. You could back off and look at a branch, even though it has exactly the same reflectance properties. The leaves have exactly the same reflectance property. You back off. Now you're looking at leaves that are all different angles. You're looking at a little bit of branch, which has different spectral properties, and you're looking at shadow. You're looking at other things. So looking at a leaf versus looking at a branch versus looking at a tree versus looking at a forest, all those things are different. The reflectance is different, and so it's very difficult to build a library of vegetation spectral properties and use that vegetation spectral properties library to map things, except very locally. All of those things, canopy, viewing geometry, illumination, background materials, because you can see through depending upon the density of the vegetation, all have effect of that. So spatial scale of the measurement is very important. If you make a measurement of a leaf with your field spectrometer, that may not relate very well to what you see from an imaging spectrometer. So when I say all vegetation spectra are similar, this is what I mean. Between vegetation, it has a peak. Green, these are stacked again. It has an absorption feature for chlorophyll here near 0.68. And vegetation scientists will talk mostly in nanometers, so 680 nanometers. I'm talking micrometers. It has features caused by certain chemical components I'll talk about in a minute here in these wavelength ranges, but then it has the 1.4 and the 1.9 water and the fall off at 2.5 because of water in the vegetation. Typically, it's this green and this IR peak that you use to recognize vegetation, and these other features in here to characterize it. For remote sensing, the 1.4 and the 1.9 are not useful, but you can tell certain things in this wavelength range between the water bands and in this 2 to 2.5 range. The mechanisms for leaf reflectance, some of it is spectrally reflected, some of it is diffusely reflected, some of it is absorbed by the leaf, some of it is modified or absorbed by the leaf structure, some of it penetrates through. It can penetrate through the leaf below, in which the same thing happens again. So what's returned to the spectrometer can be a combination of what's been measured in several leaves.
Is the IR ledge a function of photosynthesis?
Some of it is used in photosynthesis, and some of it so it's absorbed by these cell structures. Just the chlorophyll is the main thing. For photosynthetic vegetation, it's absorbed there at 680 nanometers, and that's utilized by the plant.
Which is real close to the IR?
It's right at the IR plateau. I don't know how much of the IR, well, the fact that it reflects, it's not really using the IR.
It's not using it.
Yeah, it's that red, edge of the near infrared light that's being used the most. So dominated in that 0.35 to 0.8 micrometer by pigments. The reflectance in the 0.8 to 2.5 is dominated by liquid water in the plant tissue. There's also minor features in those ranges caused by different chemical bonds, and the stretching and vibrational bond is what I've talked about for minerals applies there as well. All of these bonds vibrate in different ways, so they absorb different amounts of energy. Here's an illustration. Then chlorophyll, what we call to is the IR plateau. This is caused by the cell structure. Water, water, water. Here's a list of some of the different components. You'll see in the libraries, you'll see spectra for pure cellulose and pure lignin and pure starches and things like this. And so you can use a library to see where these features are superimposed, but they're superimposed upon this overall structure of the high IR plateau and the water vapor absorption, or the liquid water absorptions. Here's an example from that book showing some of the pigments, and these are actually absorption. These are flipped compared to what we're used to looking at, because they're measured in a different way. So where there's a peak here, this would be an absorption feature in reflectance spectrum, because these are measured in absorption rather than reflectance. So the main ones that we see in green plants are the chlorophyll A, which is, who knows which one, 657, chlorophyll A, it's probably that one. Not a very good key on this. And then there's different ones depending on the type of chlorophyll, depending on whether it's a beta-carotene, which is an orangish pigment. That's where those absorption features occur. And you can start to separate those pigments out if you analyze a vegetation reflectance spectrum in detail. Also, when there's vegetation in the water, the same kinds of things, you can start to see some of these features as well. So here's some of the components in the canopy, nitrogen-rich components. In fact, they're used to estimate the amount of nitrogen, which is an indicator of the health of the forest. Sugar, starch, oils, and waxes. The non-vegetative canopy components are important, and in fact, dry vegetation has a fairly characteristic signature. I'm not sure if I have it in here, but I'll show it to you at some point. In the shortwave infrared, it has a feature at 2.1 and 2.3, and a peak at 2.2, so it's kind of the antithesis of the mineral features that have, the minerals that have features at 2.2. I'll show you an example, but I don't think I have it right here. So one thing remote sensing technology and imaging spectrometer data can be used for in particular is to tell you something about vegetation health. You've heard probably about the red edge. You heard about the red edge? Yeah. In multispectral, where the feature shifts around supposedly depending upon how healthy the vegetation is and how well it's stressed. Well, these are just an example I did. It's actually a cute story that I won't tell now because I have time, but it basically rescued one of my research projects for geology by demonstrating that the things I was doing were applicable to vegetation by looking at, this is ozone damage in the Sierra, a low damage plant, ponderosa pine versus a high damage ponderosa pine. When you plot them all up, of course they all look the same. There's some differences here, but really nothing coherent that you can see. If you apply a technique called continuum removal, which we'll talk about in some detail in the identification stage, where you fit some kind of background to it and divide it out. We're interested in what this band looks like. Where does it occur? How deep is it? How wide is it? What's the shape of it? And these are tools I was using for geology, and demonstrated that they're applicable to vegetation.
Was that basically averaging across the wavelengths?
No, because it's actually parameterizing it. So it's just saying, here's the center, here's how wide it is, these are numbers, here's how deep it is, and then there's finally one other parameter that says how symmetrical is it, how much is to the left and how much is to the right of this band center. So you're not really averaging, you're extracting parameters, quantitative parameters, and I'll talk about that in detail. But the point here is that when you did that, all of a sudden there's a very clear relationship between the depth of the absorption feature for the chlorophyll and the damage. So this is the low damage. It has a deep absorption feature, lots of chlorophyll. This is the high damage. It has a shallower absorption feature, less chlorophyll. So you can use that to start quantifying things. And the methods, the red edge method, which only looks at one side of that band, that's the typical way that vegetation scientists, remote sensing scientists look at vegetation, moves around, and you can quantify it in the same way. The highest correlation that they had for these data using that method was about 0.7. And when I did this with the full band, the correlation was 0.985. So that convinced NASA that maybe what I was doing was interesting and useful, and they funded me, and I went back to geology. The point there being that there's a strong relationship between that chlorophyll band and the depth of the chlorophyll band and the reflectance signature. I'm going to stop there. We're right at the 10 minutes, and I'll talk about vegetation and water and so forth. And we'll get into the long-wave IR probably at the end. Questions?